This is video 11, and we'll get right into the book right away. Now we're up to Albert Einstein developed the theory of relativity, which proved that everything is relative to our perspective as an observer. Even space and time can be altered given your motion as an observer. The faster matter moves, the shorter it becomes. These are some of his findings. The faster matter moves, the heavier it becomes. The faster matter moves, the slower time moves. E equals mc squared. This proved the equivalence of energy and matter. The important point of all of Einstein's discoveries is that we view the world in a relative sense as opposed to an absolute sense. This allows for this massive variation, interpretation, and approximation of reality that we experience. So space and time is relative. E equals mc squared. This seems concrete to us. It's really made up of energy, of motion. Even the smallest amount of matter, particles can contain massive amounts of energy, such as an atom bomb. So all of this relativity and this scientifically proven fact that the universe is so much different than we are perceiving it on a daily basis is the point of all that. Entanglement is the concept that particles can communicate instantaneously regardless of their location in the universe. This is a proven fact of science by Bell's incompleteness theorem. This communication is done without the transfer of information, however, and does not require space or time. It is communication that exceeds the speed of light without ever traveling any distance. It is a holistic, omnipresent knowledge of another part of the universe in an instantaneous fashion. So entanglement is just another thing that's come about from quantum mechanics. If you have two particles in the universe, and they can be any distance apart, if these are entangled pairs, we are able to perceive one of the particles and have knowledge of another particle in any part of the universe. This really is an amazing fact. Einstein developed the theory that the speed of light is the speed limit of the universe, but this, in effect, is communication faster than the speed of light, because this can be any distance in the universe that we can know about this particle and another particle due to this entanglement. This communication is really another amazing thing about the universe. It is contrary to the way we think of the world. Moving on to Galileo's paradox, one-to-one correspondence. Both sets have equal numbers of members in a one-to-one correspondence, even though the second set skips many numbers in between. And I have to draw this out. Here's a paradox. Now Galileo, he was someone that was shunned in his when he lived. He was banned from the Catholic Church, and here's just one of his paradoxes. If you had a sequence of numbers 1, 2, 3, 4, 5, and on to infinity, and then you had another sequence of all the numbers that you could square, 1, 4, 9, 16, 25, and so forth. On a one-to-one correspondence, there would be an equal amount of numbers in both sets going on to infinity, yet this set here skips 2, 3, 4, 5, 6, 7, 8, and all these numbers in between, is an amazing paradox when it speaks of infinity. Um, you're skipping all these numbers, yet on a one-to-one correspondence, and this could go out forever, um, they would have an equal number of members onto infinity. So that's one paradox that he had. Another one was both sets have equal numbers of members in a one-to-one correspondence, even though one set is twice as big as another. Here's another one he came up with, which adds to this craziness. If you started here, then you had 1/2, and you had 1, and if this one was going from 0 to 1 to 2, so in effect these are moving twice as fast down here, and these go out on into infinity. On a one-to-one correspondence, again, there would be the same amount of numbers in both sets, yet this is proceeding out at a twice as fast a rate, because you're going 0, 1, 2, 3, 4, 5, and this would be going 0, 1/2, 1, 1.5, 2. This would proceed out into infinity faster, but on a one-to-one correspondence they have the same amount of members in each set. So that's kind of strange. Fallacies based on division by 0. This is really weird, and we just kind of overlook it, or just modify it and change it to fit in to the way we want to view the world. If you said 0 times 1 equals 0, 0 times 2 equals 0, then you said 0 times 1 equals 0 times 2, and then if you divided both by 0, you would have 1 equals 2. So we just looked at those Galileo's paradoxes, which seem to suggest that 1 equals 2, and then when we did, if we did this mathematical, by the rules of mathematics, 1 would equal 2, but we know that 1 doesn't equal 2 in our real world. So mathematicians and in class and the way they would teach mathematics is to say, just disregard that, it's not important. So that's kind of interesting. Moving on, the Big Bang. Given the theory of the Big Bang at the beginning of time, we can determine the largest possible size of the universe. You could take the number of years of the universe has been in existence and multiply it by the speed of light. Again, this is our way as humans to describe an unlimited universe in a limited way. We can make it incremental. This gives us the foundation to say the universe is 14 billion years old, for example. If we don't have a starting point, we can't get to our current point. As Immanuel Kant said, it would take an infinite amount of time to get here, which is impossible. So Kant, in Critique of Pure Reason, stated that the world must be limited, because how could you ever get to this point? There would be an infinite amount of time which would have had to pass. Therefore, time has a limit and is a limit. Without these stabilizing concepts which give us a beginning, we truly couldn't know where we are or when it is. Within this view of the world, we can at least say we are at coordinates length, width, height, and time. Without these relative concepts, we would find ourselves in the middle of nowhere. Planck discovered that light was made up of quanta in 1900, as I mentioned. This had a profound impact on the world scientific community. It seemed to support the fact that the world was therefore discrete as opposed to continuous. And we talked about that, so I'll skip that for now. 1924, de Broglie theorized that all matter has a wave-particle duality. This was the start of quantum mechanics. Then in Copenhagen interpretation. In 1928, there was this question of whether the world was discrete or continuous. They thought because of waves and double slit experiment, but really waves and quanta, waves of light, photons, travel in discrete units. So really, in our world, absolutely, the way we are perceiving the world, it is discrete. And with that, I'll stop, and then we'll move on again.